All right. In the first place, I would like to first welcome you to this presentation. And for the people who don't know me, my name is Lana Krastev, and I'm computational facilitator and also computational scientist in the research computing group here at Harvard. And my experience generally is previous background that I have is in nuclear theory and computational physics. And before coming to Harvard, I was at Lawrence Livermore National Lab, basically working on high performance, very large scale codes in the context of nuclear theory. And this is what really got me into the world of high performance computing. And here at Harvard, I'm helping researchers with various computational issues they have, helping with optimization and prioritization of various applications and everything that comes in between. So today I'm going to be talking about using containers on our cluster, and in particular, I'm going to talk about Singularity, which is a type of container technology. And the containers in recent years became kind of a pretty hot topic because they allow to do very efficient software management for the most part. And that's why this is the purpose of this presentation. So some of the objectives that we have here is really to advise you on the best practices for running containers, in particular Singularity containers in our environment, and also really to give you the very bare bone and minimum knowledge which is required to build your own containers if you need to do that for any reason. Again, we don't have that many people, so just feel free to interrupt me at any time if you have any questions, so we can make this session a little more interactive. This is a very quick overview of the main points, which I'm going to touch briefly during this hour and a half with the questions. So basically, first I'm going to give you a very quick overview of the containers, what they are, why we care about containers, how we can use them, and then give you a very quick overview on the Singularity container system itself. And basically, we'll provide also some information on how to run Singularity containers on the CAN cluster. And there are various modes in which we can do that. One of these is pulling containers from Docker registry or the SY library. Also, GPUs are a very big thing. So we're going to touch how we're going to run actually containers using GPUs. You can use also local images if you have in the cluster. And also we're going to touch briefly how to build your own containers, something which is called bind mounts, which allows you to basically expose mounts which are on the host machine. And at the end, if we have time, I'm going to talk briefly about running parallel applications, in particular multi-core open MPI type and also distributed MPI type applications. So what are the problems that we're trying to solve with the container technology? One of the most important problems, and here I'm speaking of myself, is really the deploying applications, especially when you do this on a cluster, which is kind of a very heterogeneous and complex environment. Basically, the installation and management of the software can be pretty complex. And because our environment is quite specialized and many of the software applications have a lot of dependencies, and it can be pretty cumbersome actually installing this, and the software technology which lies behind the containers actually can help with that. Also in this, the operating system installation is streamlined, which is contained for the most part in the container. And like I mentioned, many of the especially scientific applications have a lot of dependencies, and it can be very difficult and time consuming. It may require a lot of iterations to install actually all the dependencies and get at the end your application running free of any problems. And obviously there are also other ways to do that. like we have, the easy build system, and also some other, systems like Conda environments and stuff, which provide this capability. But the containers actually are very unique in this respect. And also, for example, if you want to install something which is like a binary, or if you want to install something that you can do, let's say on your Ubuntu machine, for example, like doing sudo apt get install won't usually work, because this requires root privileges, and the containers are one way actually to overcome this difficulty. Another very important problem that we, the scientists in general, have, and also the researchers, is a matter of portability and reproducibility, because science needs to be reproducible. In other words, it doesn't matter on which platform you run your applications, you better get the same results. And the container technology allows you actually to solve this problem, because it can pack your applications in a very kind of a compact environment, and you can give, let's say, to a collaborator, the exact code and the exact workflow that you used, containerized in container, and then they can run that and get exactly the same results. So that's why this is very important. And also, as a user, basically, the researchers can minimize the time and the effort which is usually required, to let's say move the workflow to a different platform, because you need to, if you don't use, let's say, the containers, you need to install all the dependencies and everything else, and this is definitely time which can be much better spent on scientific productivity and doing actual science. The other thing which is very important as a problem that the containers potentially can solve is really the resource contention security, because the containers, they really containerized your environment, and they, by their very nature, actually, have this resource contention. So don't allow users to mingle what's going inside the container of application which is run by somebody else, so to speak. And that's why in a multi-tenant environment like our HPC environment, this is very desirable. And also the containers provide the solution of the problem to the security, because users cannot see other users' applications and stuff, like we mentioned here in this slide. So like I mentioned, the way to resolve this problem is really using the containers. Like we say here, they provide a potential solution. They are quite easy to deploy. And the important thing is for example, the container can be built on a totally different platform, on a totally different machine. And then when you copy the container to our software environment, you can run it. They're quite easy to publish also. And like I mentioned, they're quite portable, with some exceptions that you have to keep in mind. And in particular, I'm going to touch briefly the problems that may exist with especially MPI type applications, where you need to be a little more careful when you build your containers. But anyhow, they can greatly simplify our workflow as software developers, and also potential users of software. And this is the major reason why we're using the container technologies. So this is a very quick overview. Maybe you already seen some of these terms that I have here. Here, basically, I'm just mentioning some type of the containers, and also supplementary technologies. We just make sure not to really confuse, for example, the C groups or the control groups with the container. They're mostly considered to be kind of a supplementary technologies, because the C groups allow you to have kind of a fine-grained basically distribution and management of the computational resources, like memory, number of cores, CPUs, and so on. Also, you're quite used to different Python environments like the Conda environment or Python virtual environment, which allow you to containerize to some extent or to isolate. Maybe this is the better word for this, your computing environment so that it doesn't mingle with other applications that you may have in the system. So the real type of containers are like Docker type of containers. Maybe you heard about Docker or you already use it. These are the real containers that we're going to talk about, and in particular about Singularity. Virtual machines, they're another type of technology which allow you to have like a total replica of a standalone PC. For example, it contains everything starting from operating system, the Linux kernel, and so on and so forth. And on top of that, you have the applications that you need to run. The virtual machines by themselves, they are not really containers, because actually the virtual machines, they can contain containers. Actually, you can use a virtual machine to build containers. So basically, the type of containers, this is just kind of a general, sketch over here, where we list some container technologies which are more oriented towards the general purpose and microservice oriented, and also a type of containers which actually solve problems which are typical for our HPC environment. And in this, we also have the Singularity type of containers. And the important thing about this, because they provide actually workload management and can be very easily managed with, for example, Slurm, which is the job manager on the cluster. And also they don't require actually privilege escalation, because to run Docker containers, you may need actually to have root privileges and so on. For example, in an environment, HPC environment, basically Singularity is a type of container which doesn't allow to have root or admin privileges. Although to build the container itself, actually you need to have root privileges, and we're gonna get to this point when we get to the point of discussing how you can build containers. Okay, so let's just move ahead. So what is really Singularity? Singularity really provides a container runtime and kind of a platform which allows you to build and also to run containers in a HPC environment, which by its own nature is multi-tenant or multi-user environment. And here we list some important aspects. There's no need to have elevated privileges, although, like I mentioned, root privileges are required to build the actual images. Each application can have its own container, although nothing can stop you actually to build a container, which can have several applications. But as you're going to see, some of this can have can be quite sizable in terms of actual size. Going from 100 megabytes to several gigabytes. So maybe it's better just to have a single application in the container, because it's quite easy to build this. The users can have exactly the same user IDs and group IDs when running the application within the container. And basically, the containers can be executed from local image files that you may have on your platform, like on Canon. If you don't have images, you can grab images from the Docker registry or some from the libraries which are available, which are great resources for Singularity containers written by many users. If you go to this web page over here, we have some resources over there. Let's just click that actually. Oops, broken link. Let's just go here and go to RC. think we have this page. I just have to fix this in the presentation itself. Okay, Singularity. Yeah. So that's actually the actual page I just wanted to show you. It gives you some basic information about how to run Singularity on the cluster with also some examples. This is the link that I wanted to show you. Here we also have the official documentation of Singularity. So let me just show you some specific examples, because this is really the best way to do that. And for example, we're going to start by looking at how to run Singularity container by pulling an image, existing image from the Docker registry or the Docker hub. So what you do, the procedure that we recommend is first to start interactive session. And if you're already familiar with the cluster, you know that you can start this with doing just slog. And then, for instance, you can go to the test partition, request some memory and specific time for your session. Then what we recommend, because these images actually can be quite sizable, just going to your Scratch directory. The Scratch environment variable basically currently points to Holy Scratch 01. And then you go to your specific space and your user space. And this specific example here shows how to pull the very latest version of TensorFlow. And I'm going to go through the steps here, and at the end, if we have time, basically we can do an actual walkthrough. Basically, do the same example in the shell. So this will pull out the latest version of TensorFlow from Docker, and this will be a CPU version. So this example shows you how to run the TensorFlow deep learning library on a CPU node. So when you do that, basically you will see in your space the image which is named TF 2.7 or 27 underscore CPU dot Singularity image, and we put it here from the Docker registry, and we give it the label latest, which is the latest really version of of the TensorFlow library. And then we can actually run the actual image, and because we are in an interactive mode, we can totally run it on the compute node where our session lands. So you just start Singularity, like Singularity exec, and then the name of your image, and then the actual command, which is Python. And this will open up a Python shell, and then we can print actually the TF version or the TensorFlow version, which is 2.7. You can actually run some example. We can grab some examples from Keras, and here what we do, we run an example which do basically Singularity, which does image classification of the MNIST basically training data set. And here we get some results. But let me show you actually how this works in practice. Just gotta go to my session very quickly. Show how this works. Just can start. This. And I'm just going to run it on the background and see how this will go. can you see my screen well, or it is too small?
I can see it fine. I don't know about everybody else, but it looks good to me.
Okay, perfect. Thank you.
That looks good.
All right. So yeah, so it takes a little time to allocate resources. And in the meantime, I can do something else. Quickly, oops. Just start one more shell. Yeah, we got some idle nodes. I'm just going to message for this. All right, and go to my home scratch. Oops. Space. Singularity. Oops. Happen. Examples. So I have here some examples, but what I'm going to do, I'm just going to pull. I'm going to run actually one of these and see how this works. So I'm just going to pull Singularity here. And okay, Docker. All right, so let's remove actually this. All right. So as you can see, actually, the actual process of putting the image started, and I'm going to go back to this. Basically, I just want to put it on the background while I'm going through the presentation. So so this is with the CPU application. Very similarly, as you know, the real power of TensorFlow is actually when we run on a GPU node. So for this reason, we need to grab a GPU version of TensorFlow. The very first thing we do, we have to actually land on a partition which is capable to do GPU computing. So we start interactive session on our GPU_test partition. And here I'm highlighting in red the options which are relevant to GPUs. So we do G reservation GPUs, and we actually reserve one GPU. Again, the memory is 4 gigabytes, a single node, and 60 minutes. So next, pretty much you do exactly the same thing. You go to your scratch space, and then you run exactly the same command, but the version of the GPU that you're pulling is basically a GPU version. That's why you have to specify this in the label over here when you pull this from the Docker registry. And pretty much everything else is the same. Coming to the execution part, where to execute the Singularity image in a way so that it can utilize the GPUs on the host, you need actually to include this option, which is --NV, which makes sure that your image can use the GPUs which are on the host machine. Let's see what happened here. All right. So pretty much the image is over here. So we got our Singularity image, and I just run it. I'm just going to go actually back here because I'm just going to run it with this command. Something's going to happen. All right, so see that actually started working. It just grabbed the example and it started actually doing the actual training using the data set, and it will run for 15 epochs. All right. So let's go back to our GPU example. So pretty much like I mentioned, this example here does exactly the same thing as the example that I'm running currently, but this would be run on a GPU. And like I mentioned, actually the actual command for running the Singularity image, which here will be a GPU version of TensorFlow, it's exactly the same. But in order to use this, very important, in order to use the GPUs on the host machine, you need to use this option up here, and --NV. Let's go ahead. So now we're moving to a part where we will be talking where you find the actual images. Here we discuss how you can pull images from the Docker repository and from the Docker registry, but there are also quite a few different places from which you can pull images. So the very first thing is actually to do this preparation part, which is to start again a interactive session, go to your start space, and then this is an example which allows you to pull from the Docker registry. We already showed that. You can pull also from the shub library. And this is the command actually which would show you here the example how to pull from this library here. And the important point is really to use this specifications over here after the pull command. And these are some specific examples. The important point to remember about the shub library, right now it is a read-only archive because I think they are transitioning to something else. Previously, it would allow you also to store your images there, but I think the successor of the shub library is the SYLab, which is currently operational, which also has capabilities for building your images remotely when we get to this point. So this example, for instance, here shows how to pull from SYLab library, and for instance, this specific example would pull a tensor, not TensorFlow, but this is a version of Ubuntu 21.04. And then the good point is that you can actually use this image as a starting point, and you can install in the image, for instance, other applications that you want to run. Another very important registry which I would like to talk about is the NVIDIA NGC registry, which in particular contains many images for various applications and also AI libraries, which are specifically tuned to the NVIDIA GPU cards. So it is a really great resource. And for instance, here we show the example of pulling again image of TensorFlow, which is built so that it's totally compatible with NVIDIA. Let's see what happened here. I just want to go back. Yeah, so this is totally complete. So as you can see, you can run the TensorFlow library on various models and codes that you may have. And in this way, you totally skip the installation of TensorFlow, which can be actually quite difficult if you don't know exactly what you're doing. Okay, so this is how the NGC portal looks like. If you go over there, you will find many different applications. Let me just show this actually in action. If you go here, you see containers. Yeah. So if you go here, you can basically search. You have PyTorch, you have TensorFlow. You have many applications which are specifically tailored down to GPUs, like, for instance, many applications like GROMACS, like OpenFOAM, which are applications for molecular dynamics and many others. So you can find many applications which are already available as containers, and you can totally pull this on the cluster exactly in the way I show you, and you can use this. All right, let's just go back to the presentation. So this is that.
Playman,
Yeah.
I have one question. So
Okay.
for the Docker Hub, is this the same one we use for the Docker images, or it's a different URL?
You mean actually the registry? It is actually a different one. Yeah, that's actually a different one.
No, for the Docker Hub. It's the same one we normally use for the Docker, right? It's the same one, or it's a different?
You mean the
Docker Hub?
Yeah. No, that's actually a different one. That's actually this is the NGC catalog. Basically, this is a different.
No, my question is whether the Singularity has a different version of Docker images, or it's the same one.
No, they're exactly the same. I got your question. Okay. Yeah, basically these are all. Yeah, if you go here, you can see. Oops, I think I download something. I think you can.
So just to answer your question, Wilson,
right.
It's a Docker registry for Singularity. We are converting them to Singularity images. There is no as such Singularity registry. So I think, they are working on it, but I don't think.
I think actually the SY Lab provides this capabilities to some extent, because they have already some Singularity images. For example, if you go to, where was that? If you go back here to here. Let's see. Yeah, if you go here, you can look actually for applications which you can pull, right? And these are already totally Singularity images. So this is something similar to, to Docker Hub, I think. But you have to bear in mind that this is still, alpha. It's not really kind of it's not yet a fully operational thing. They're still working on that. But basically, the good thing about this this cloud service is that it allows you to build remotely Singularity images, because currently you can't really do this on the cluster, because building the Singularity images itself requires root privileges. As a general user, I mean, you in particular, maybe you can build, but basically, general users can't really build Singularity images on the cluster. This can be built remotely, but there are a few steps that you have to take into in advance in order to be able to do that. And I'm going to get to this point. All right. So, is that is it answer or? Yeah.
Yeah, that's good. Thanks.
Yeah, but basically, like Raminda mentioned, these images that we have in the NVIDIA portal here, they're totally Docker images, but basically when you do the Singularity pull command, it actually gets the Docker image and converts this into Singularity image. So it does this automatically, for you, and you don't really need to, to do that. Yeah. So, okay, so let's just continue because we have quite a few things to cover. So the next step that I just want to touch briefly is really, to run images that you may already have in the cluster. These are images that you may have built, elsewhere and transition to the cluster, or you may try to use images that we already have in the cluster. For example, if you go to this directory over here, you will see that we have quite a few images, which also are searchable in our portal. Just go to this. I'm just jumping back and forth. If you go over here to our portal and choose Singularity only, basically it's going to show you, the applications that we have, which are Singularity based, and also give you the actual commands to run this. And let's just go and show you this. If we go to portal, click on modules. Initially, by default, it shows you all the applications built under all platforms, but you just can leave only the Singularity thing. And you will see what we got here. So these are quite a lot of different applications, and it actually tells you the command that you can use, to run the application. So let's just go back here. All right. So if you have an image, you simply can get again interactive session. Go to your Scratch space. Here, just get an image of the IDL, which is interactive data language. And this is just nothing special about IDL. I'm just using this as an example over here. And then you run Singularity with that image, and you start IDL interactively, and you get actually the IDL shell. And this is very, very sleek way to run various applications. Okay, we already covered that point. So we come to interesting point here. Basically, Singularity images are quite sizable, and when you pull images from various libraries, these are stored locally in under .singularity, which is in your home directory. And the problem with this is that they can become, quite sizable. And let's say, for example, if you experiment building a single image, basically it may not be very problematic for you, because the image get cached, and then you don't need to download this every single time when you actually make changes to the current image that you're building. But if you pull many images, actually, you may very quickly run out of space, because these images are quite sizable. Like I said, in our home directories, for example, they're 100 gigabytes. For example, under my Scratch space, I have something like almost 10 gigabytes of cached data under Singularity. And you can display what you have. If you do Singularity cache list, it will display basically what you have. And then you can actually see what you have by running a simple ls command on that folder. It will show you this, and it will show you the size. If you want, you can clean that by doing a Singularity cache clean. And if you need, for some reason, these images, it's very easy to repoint that to a different location by using the Singularity underscore cache dir environment variable. Or another way to do that is when you're pulling images, just to use the option. Nathan actually from our group mentioned this. When you use double dash disable cache option after doing Singularity pull and this option, this will actually disable the cache and save you lots of space. So pretty much this is about the cache folder, and there's also quite a lot of information under the built environment in the official user documentation of Singularity. Okay, so let's say you already have the images, you build it or you pull it from somewhere. Let's just touch briefly the actual running of jobs. Many of these applications can be run as any other applications. The actual Singularity images can be run as other applications by using the regular .job submission scripts that we use on the cluster. For example, this here show you a kind of a very simple example of doing this. You give some name to your job, which is a Singularity test, reserve one, core, run this on test partition, reserve 4 gigabytes of memory, and give it 8 hours. And you can use one of the commands, Singularity run my image, where the Singularity run would run, some kind of a section that you have in your Singularity image, which would run the actual application. Or you can use the Singularity exe my image and the actual command of the application, which is within the image. So these are two different ways, and this in general would depend on the specific application that you are running. So let's just come to the point of building the images. Like I mentioned, you can build these images in some other place or pull them to our environment from like we saw from Docker registry or some other libraries which contain Singularity images. So in order to be able to build a Singularity image, you need to have spec file, which here is called the definition file. And this is a very simple example which would build, which would install the Vim, which is based actually on the Ubuntu environment, on the Ubuntu Linux flavor. So here first we have some header where we have to specify the way how you do the bootstrap thing. If you do this, let's say on Linux environment, for example, like ours, like CentOS, the very first thing is to make sure that actually the dep bootstrap is installed on the host machine itself. This is the operating system name. In particular, this is the flavor of Ubuntu. And here we point this to the mirror of Ubuntu. And this section here tells actually what happens with the Singularity run command. And if you do simply Singularity run, the image which is resulting from this definition file, it will run simply this what happens when you run the container. It will simply print this, and then we have some installations that we do on top of this Ubuntu image. we first update that, and then we install the VM editor, and then we simply clean that, and pretty much that's all. There are various ways to do that. In general, you have 3 different options to build your images. One of the ways is to build this locally. But like I mentioned, you need to have root privileges. And in order to do that, you need to have access to a Linux machine. Or you can do that, let's say, in a VM machine that you, for example, built on your PC. And you can use software like VBox, for example, to build a VM, which you can use to build your images, for instance. And once you have that, to build the image from definition file, you simply run this command, Singularity build, and then the name of the definition file on your computer. Like I mentioned, this would require root privileges. So maybe if you run this as a normal user, you should have sudo. If you run this under root, this would be the command that you run. The other way to do that is to build images remotely. Like I mentioned, this service over here, this cloud service allows you to do that. But to do it, I haven't really experimented with this, but it is possible to do that. Basically, you need to register and get a token, which is stored in your home directory under .singularity, like sy-libs -token. And then once this is done, you simply run the usual thing. You start interactive session, you go to the scratch space, and then you do Singularity build, which is exactly like here, but you do that with the remote option. And what's going to happen is that this will create the definition file and build the image on in the cloud, and then download it back to your local folder. So this is the way to do it on Canon, on the cluster. Another way to do that is to build your images locally using Docker, which I mean locally on your own machine. You can install Docker on your PC or Mac computer, and then build images that you want. And then you have two ways to proceed from there. You can export the image to the Docker Hub and pull it from there, like in the way that we described that previously, or simply use this command, docker to Singularity. If you go to here, it has actually this application which you can install, and then you can use it to convert the resulting Docker images to Singularity. And once this is done, you pull the image to the cluster in Singularity, or simply CSP or rsync to our environment and use it. So that's the way to go. Let's see what else. Another important point is, I just want to touch this briefly in the time that we have. This is the bind mounts. Because by default, all the directories in the Singularity images are read-only. And in addition to that, some system directories are not available. Let's say you may have some data on the host machine that you want to be visible by the Singularity images. And the way to do that is actually to use the bind option or the B option, the block capital. And this has this specific the specific options to do is actually to include first the host directory and then the container directory. So what it does, it maps the host directory to the specific container directory, like shown here in this specific example. let's say on the host machine, if we have directory data, we get its content by simple ls, and then we bind the data directory to the mount directory within the container, and we do ls on the mount directory within the container, we're actually going to see the content which is under the data directory on the host machine. So on Canon, what we do, we automatically map the end directory, the net, and the scratch directories, which are in the images, which by using the bind mounts. And if you go here to this page, you can find all the information in more details, which actually discuss this topic. So in the minutes that I have, I just want to touch briefly the topics of running parallel applications by using Singularity. And in particular, I'm going to be talking about two types of applications. One of these are multi-core or OpenMP type of applications, and the other type of application are distributed applications or MPI applications. So what we're showing here, this is a very simple, example which builds a Singularity image of a OpenMP application, and this specific OpenMP application is, if you just go here, I just put it there as an example. It's a very simple, C code which computes a very simple dot product in parallel, and does this by using OpenMP, where OpenMP is parallelization, which is used on the single box or on a single machine via shared memory parallel model. And basically, you build this, you have this definition file, and then you can build your image, and then you can run it. And this is a simple script which would allow you to run the Singularity image and the image and the application within it. So the important point here is, because this is a OpenMP application, is actually to reserve a single node and then to reserve several cores, in this case 4 parallel processes, which are all physically on the same machine. And then we use exactly the same OpenMP paradigm. We export the OpenMP number of threads, command, which here is equal to 4, and the store underscore CPU underscore per task environment variable will expand to get actually the number 4 here, which is this number of cores that we reserve. Then we simply run this. We run it like we usually would run a OpenMP application, where after, let's say, if that was a native application, we would skip, this part. But now we include this part over here, which is the Singularity exec, and then the resultant image, and then the actual executable, which is copied within opt/bin directory. And it's not very important. It simply sorts the output, which in this case would be simply this. So this is the global dot product. We run the application on 4 threads, and we get the local, and then we get the local dot product actually from each thread. So pretty much that's all for this. And let me just go to running MPI applications. There are several ways really to run MPI applications with Singularity. And if you go to this website over here, it contains quite a lot of information and the details which allow you to do that. But here I just want to mention that the mode that we really recommend is using the hybrid mode of running the MPI applications within the container, which here is really using the MPI run from the host and the application from within the container. The important point here is that the flavors and the versions and also the compile options on the host and the container need to match exactly to get really the best performance. And this is what I have here is simply a simple example which actually shows how to run that. And the specific application that I have is just a Fortran code which simply just outputs the rank of each MPI task that we have. And the full example is over here. So it contains the MPI code, also the Singularity definition file for OpenMPI, and also for MPI CH, which are two different versions of two different flavors of MPI, and the actual commands which are used to build the images, and also the actual execution of the files, the resultant images that we have for the case of OpenMPI and also for MPI CH. So I think pretty much that's all I have. So we're open now to any questions you may have. All right.
Flamen, you mentioned there's